Data quality is a recurring theme for this module, and in this lesson we'll discuss QA/QC terms and steps we take to reduce data uncertainty in lab analysis of our water samples. We covered these terms in the previous module, but it's fine to mention them again briefly because we want our data to be right, and so accuracy and precision matter. Accuracy is the degree of agreement between an observed value and a true value, whereas precision is an indicator of how closely replicates match. In the lab, we use check standards, for example, to assess accuracy, and duplicate samples to assess our precision. Accuracy and precision are the two most common terms associated with data quality, but they are not the only terms. Really, the top 5 terms are accuracy, precision, representativeness, because we want our sample to represent the population we're sampling, comparability, because we want our data sets to be comparable to other data sets in terms of the level of quality, and completeness, which relates to how many valid samples we collected compared to how many we planned to collect. We obviously also want to minimize bias, ensure reproducibility between labs and repeatability within our own lab, and pay attention to our equipment's sensitivity or its detection limit. We make sure our lab analyses satisfy these components of quality by practicing lab QA/QC processes. For example, check standards, duplicates, spikes, and blanks. Starting with, what is a sample blank? This is a high purity water sample that's analyzed along with your other water samples to detect contamination. This high purity water should have nothing in it so that it should come back at 0 in the analysis if there's no contamination in your sample process, which can happen a variety of ways. Honestly, I did not realize there are all these different kinds of blanks, but the place along the process that you use this sample of high purity water determines what that blank will tell you about contamination. For example, we always use instrument blanks in every analytical run. Every 10 samples on our auto analyzer, we include a blank of just high purity water to make sure the equipment hasn't drifted during the run and to detect any sources of instrument contamination. If we took some high purity water in the lab and filtered it along with our other samples we had collected, and then stored that filtered blank along with other samples prior to analysis, that would indicate to us any sources of laboratory or method contamination. If we took a beaker of high purity water out to our auto sampler in the field and had the sampler collect some of that water prior to collecting some of its regular water samples, that would be a field blank or an equipment blank, depending on how that sample was handled. I've never done that, but I just hope this illustrates the importance of blanks along the water monitoring process. Another QA/QC procedure is the use of duplicates and replicates. When I talk about duplicates, I'm almost always talking about a lab duplicate where we split one sample from the field into 2 vials, then analyze those 2 vials separately. Remember, this is a way to check the precision of our analytical process and equipment, because those 2 analysis results should be very close to each other. Taking a field duplicate is a way to document the precision of your sampling process. This is where you collect a second sample at the same time as your original sample, and then transport, process, and store those 2 separate samples the same. A field replicate or field split is a similar idea to a field duplicate, but is slightly different. This is where one sample is collected, homogenized, and then split into 2 samples. Often the 2 samples are sent to 2 separate labs. How do you know if the 2 duplicate concentrations are close enough? What is good enough? You calculate the relative percent difference. This is the initial sample concentration minus the duplicate sample concentration divided by the average of those 2 times 100. My rule of thumb is that we want duplicates to be within plus or minus 10% of each other based on this math for relative percent difference. Notice, in relative percent difference, you divide by the average of the 2 samples rather than dividing by just your initial sample concentration. This is because neither sample can be considered the true concentration. In assessments of precision, like duplicates provide, we do not assume one value is truer than another. In assessments of accuracy, however, you do compare to a certified or a known concentration. For example, like when you use check standards. A check standard is where you analyze a known concentration within your analytical run. Often your check standards are concentrations from your initial calibration curve, which is usually done at the beginning of the run. For example, these top rows were the calibration curve concentrations in this run, and you see those samples repeated as check standards here and here. You can use different check standard concentrations throughout the analysis run to look for equipment drift across all concentrations that you've calibrated for. For example, towards the end of this run, you see higher concentrations being used as the check standards. And sometimes we run check standards using purchased solutions with certified concentrations. For example, you see the solution of 25 milligrams nitrate per liter. Check standards are assessed using a similar equation to duplicates, but this isn't a relative percent difference. This is just the equation for percent difference. And the difference here is that we do have a true value to compare with when we're using a check standard. But similarly, we're looking for the result of that math to be within plus or minus 10%. A spike, more formally called a matrix spike, is a little bit different. This is where we add a tiny volume of a solution with a known concentration to a sample, and then that sample is then analyzed. This spike sample allows us to assess if the sample matrix, or basically the makeup of the sample, is influencing the results. The trick with spikes is that you want to use a pretty high concentration for your spiking solution because you want to create a spike in the concentrations you're seeing be spit out of your analytical equipment, but you don't want to notably change the actual volume of the sample. The calculation for spikes is to calculate a percent recovery. That is the analyzed concentration of the spike sample minus the concentration of the unspiked sample, and then divide that by the concentration of your spiking solution, all times 100%. You want the resulting values or resulting recoveries to be close to 100%, for example, 100% plus or minus 10%. The final term here is detection limit, but a tricky piece of jargon is that when I refer to detection limit, I technically mean limit of quantitation. The difference is that detection limit is the minimum concentration an analytical process can reliably detect. That could be different from the limit of quantitation, which is the minimum concentration a lab can report with confidence from a given analysis. Jargon aside, in many cases and in my lab, detection limit refers to the concentration used for the lowest standard on the calibration curve. So if the calibration curve goes down to 0.10 milligrams nitrate nitrogen per liter, any concentration that the machine spits out below that concentration is considered below detection. Now I'm giving you a quick and dirty on this, and if you really want to dig in, you should sit down with your neighborhood analytical chemist, which I'm sure you have, because these details do matter, especially when you're dealing with concentrations that tend to be very low, like when you're doing dissolved phosphorus in tile drainage water. My lab's detection limit for dissolved phosphorus is 0.01 milligrams per liter, or 10 to the negative 2. And at some of our sites, many of our samples come back at that concentration or lower. This raises the issue of data censoring, or essentially how do you handle samples that come back below your detection limit. Options here include replacing that sample concentration with a value of 0, replace it with a value of 1/2 the detection limit, replace it with a value that is the square root of the detection limit, or replacing those sample concentrations with the detection limit, as we did here in this study. All of those options introduce uncertainty in your data, and the trick is to select and justify the best approach for your application. That's the end of the slide portion for this lesson. But if you're going to be doing the homework, I highly suggest you watch the supplementary video, which goes through how to actually calculate some of those metrics for an analysis run like we just discussed. See you next time.